Okay. So we begin the main event. For the first talk, we have a doubles team playing. I would like to introduce them. Ben Baumer, who you saw a picture of earlier, is a professor in the Statistical and Data Sciences program at Smith College. He's been a practicing data scientist since 2004, when he became the first full-time statistical analyst for the New York Mets. Ben is a co-author of The Sabermetric Revolution, Modern Data Science with R, and the second and third editions of Analyzing Baseball Data with R. He'll be, his partner will be Sarah Susnea. I don't know, hopefully I did that well. Is a recent Smith College graduate, where she studied statistical and data sciences. During her undergraduate studies, she contributed to several research papers and tutored her fellow Smithies in statistics. Sarah enjoys leveraging her data science and statistics knowledge to tackle questions about the world around her. Welcome.
Maybe Scott can give you. Sure. And you only need to press the button.
Okay. So you can
okay. Hello?
Yep.
Okay, great. Thank you, Mark, for drawing attention to my increased gray hairs. I really appreciate that. It's Can you hear this okay or no? Is that good? Okay. Really appreciate drawing attention to the gray hairs. That's nice. But I do want to thank Mark and Scott, actually. So it was, I guess, at the first NESSIS. I think, with all due respect to my friends from Carnegie Mellon who are out there, I think this conference has really been kind of the backbone of this field of academia. And I've always appreciated coming here and hearing all the great talks. And it's also just a really accessible conference, I think, for students and other people. So thank you to Mark and Scott. Can we do a little? Yeah. All right, so we're here to talk about reward systems in sports, and the question is, who's the fairest of them all? So this all got underway, I guess it was 2 years ago now. I wrote a thing. I was on sabbatical, and I was serving at the time as the interim editor-in-chief of the Journal of Quantitative Analysis in Sports. And it seemed like I was getting a lot of papers that were presenting new methods or point systems or rule systems or whatever that the authors claimed were more fair than the status quo. And it just seemed like sort of an odd confluence of like, why am I getting so many papers about this? And as I was reading the papers, it kind of stood out to me that we weren't doing a great job of like defining what we meant by fairness. And so that sort of got me thinking about this. And I wrote a little editorial note for JQAS talking about this. But at the time, one of the frames, so I'm not like a philosopher or an ethicist, but one of the frames that made sense to me, is this cartoon here, distinguishing between equality and equity, right? Which are two different ways of like thinking about how something might be fair. And I think it's nice that we're playing baseball in the background on this image, so there's already like a clear sports tie-in, hopefully. So here are some examples of papers, and these are all just like in the last few years. But this one, fair world para masters point swimming for swimming. Are the handicaps fair in this Dipsy race? 2024, improving fairness in Swiss system chess tournaments. This one is about reducing unfairness in men's doubles. This one is about a fair 2014 World Cup. And it just goes on and on. These are all just from the last few years. And again, like in our literature review, like there's lots of papers talking about fairness in sports. Okay. So it's like we're talking about fairness in sports, but we're not doing a great job of defining it. So how might other people think about fairness in other contexts? And Sarah's going to tell you a little bit about some of that.
Yeah. So we had this finger on the pulse of this question in sports analytics, and we decided to turn to fairness in machine learning to kind of like structure our exploration of this question in sports. I think so. Do what? Yes? Okay, sorry. Anyways, so possibly one of like the biggest examples of fairness in machine learning is this COMPASS predictive algorithm developed by a company called Northpoint. The goal of this algorithm was to assist judges in delivering sentences for defendants. So we have some data here, but ultimately what the algorithm attempted to do was consider if an individual did recidivate or commit a crime within a 2-year window, and then predict the likelihood of them actually committing a crime, again, to inform judges in their sentences. So we have a Y.
I'm so sorry. Can I fix your mic?
Yeah. Thank you. Okay, does it work now? I guess so. Anyways, so we have a Y and a Y hat, which are predictions, and then also an A, which is a protected class. In the COMPASS example, this is a defendant's race. So ProPublica is like an investigative organization, and they picked up on this algorithm and decided to launch their own investigation, and ultimately found that ProPublica, or that COMPASS, was predicting different false positive and false negative rates for white and African American defendants, and took an issue with the fact that COMPASS fails to both demonstrate error rate parity and demographic parity, meaning that the algorithm is treating white and black defendants differently and punishing black defendants at a higher rate by categorizing them as false positives. Now, Northpoint catches wind of what ProPublica has published and responds with a 39-page rebuttal, arguing that ProPublica is actually misrepresenting their calculations and that COMPASS instead demonstrates predictive parity, so that their algorithm actually predicts, or that given that you are positive, you did not actually commit a crime. They basically argue that their numbers are representative. So there's like a very large literature and nebula of ideas and concepts and calculations around fairness in machine learning. And when we started investigating this, we had to spend a lot of time and like brain power trying to reconcile all of these ideas together. But this book, Fairness in Machine Learning, actually does a pretty good job at like taking this vast domain and boiling it down into 3 main ideas. So there's independence, separation, and sufficiency. And so to define these ideas, independence or disparate impact essentially asks that the probability of being a positive instance is independent of your protected class. So in the COMPASS example, the probability of being labeled high risk should be independent of a defendant's race. And we can relax this requirement, as well as the other 2, by setting an epsilon small positive value so that the 2 probabilities no longer need to be equal in order for us to assert that this condition has been met. COMPASS actually fails this. Separation asks that the true positive and false positive rates be about the same across the 2 classes, and COMPASS fails this as well. And then sufficiency, or well-calibration, essentially asks that your model be representative of your data. So here, it's that the true positive rate is the same. And here COMPASS passes, which is kind of the whole crux of Northpoint's argument. So that's kind of some conflicting information there. But somebody else thought about this and proposed an impossibility theorem. And so John Kleinberg essentially found that unless your base rates are the same in your data, you can't actually satisfy all 3 of these criteria at the same time, which insinuates that you have to choose or prioritize one criteria over the others because you just can't have all 3. So to summarize the COMPASS argument, ProPublica investigates COMPASS and argues that the algorithm is biased because it lacks error rate parity. Northpoint responds and says, okay, but it's well calibrated and represents the data that we used. And Kleinberg sort of mediates this argument and says that, well, your base rates aren't the same, so you're both right, but you're both wrong. And so we still don't have an answer on if this algorithm is fair or not. So to try and answer this question, or others like it, we decided to build an R package called Fairer. Fairer will use Yardstick and MLR3 software, so existing infrastructure. It will compute these 3 scores for you, for your data, using the mean absolute difference across the groups. It will also provide some visualizations to help you explore what exactly these metrics mean, and will include some like pre-loaded data sets to get you started in your exploration of these concepts. And it is also tidyverse friendly, as you can see here. So We can take our compass data, write a simple mutate statement to set up our y and y hats, and then group the data by race. And then we can pipe our transformed data into the fairness cube function and get independence, separation, and sufficiency calculations, which match what we saw earlier. So that's great. We have all these numbers and this data science that we can do. But like, what does that mean in the real world? What are sort of the consequences of these numbers? So our fairness and machine learning book that we have been referencing also answers that question and defines a few views. Firstly, the narrow view, or the idea that people with similar qualifications should be treated similarly. This commonly manifests as the idea of a meritocracy and ultimately places the onus on an individual to go out and achieve those qualifications such that they can be compared against similar people at points like college admissions, for example. The broad view, on the other hand, states that people of equal ability and ambition should have similar chances. This places the onus instead on an institution like government, for example, to provide those resources necessary for everyone to go out and achieve what they're hoping to achieve. So this is the idea that like all schools should be equally well funded. And then there's a middle view which kind of like combines the two ideas, and it argues that at certain moments, again, such as college admissions, we should adjust for past injustice to when evaluating people against one another. Until fairly recently, this was like a common interpretation in the US, but one infamous example was struck down in 2023.
Okay, so this is a sports analytics conference. I'm sure you came here to hear about sports. So what does this have to do with sports? So I think the first part of what we're hoping to achieve with this is just providing vocabulary. This is kind of like translational work where you're taking ideas from one discipline and porting them to another. So just to pick a couple examples from some of the papers that we listed earlier, this is an excerpt from this paper by Pollard et al. But two equal pairs should have as close to an equal chance of winning as possible. Seems reasonable. But perhaps instead of that, we could say something like, we have a broad view of fairness. And maybe we're focusing on sufficiency as one of the criteria that we're going to optimize because we know we can't necessarily have all three. As a second example, and notice like how different of an interpretation of fairness we already have in looking at this quote. So a swimmer with no arms should be able to compete against a swimmer with one or two arms. But if two athletes with the same disability compete, the more skilled and fitter should win. Right? So I think like in reading all these papers and thinking about these questions, I think one thing that has stuck out to me is that people's definitions of fairness seem reasonable. But as we just heard, like they can be mutually exclusive. And that's where it gets hard. And that's why I think we have to be precise. So again, instead of something like this, maybe you say, well, we have a middle view of fairness, and we're focused on separation and sufficiency at the expense of perhaps independence. As a third example, in which these authors are trying to create a system that is fair across gender distributions, and they're asserting that women generally are slower than men. Again, maybe we can say we have a middle view of fairness, but we're focused on independence as the criteria that we're going to minimize. So I think part of what we're trying to achieve is just like moving the conversation forward in a little bit more of a precise and technical way. So here's a couple examples of how this might be used in practice. This is the data from the Connecticut Sports Analytics Symposium. We're looking at called strikes in Major League Baseball. So we know whether it was actually a strike or not. The question is whether it was called a strike or not. And in this case, we're looking at left-handed versus right-handed batters as being the protected class. That's not a protected class, but it's a binary distinction that we can make just to kind of illustrate how this method might work. And you can see that in this case, all three of the numbers, so you want those numbers to be close to 0, right? That's being fair, according to these definitions. And this is the sort of exception that when the base rates are the same, you can achieve fairness with respect to all three of these criteria. Right? It's when the base rates are not the same that the impossibility theorem kicks in, and you kind of have to pick and choose. But in this case, we have all three, which is good. Umpires are fair. But here's a different example. And here, like the so I built a classifier for the Hall of Fame. It's a very simple classifier. It's like a decision tree. How good this classifier is like not the point. I'm just trying to illustrate how the method will work. But it's a simple classifier based on the total number of hits, home runs, awards, strikeouts, saves, and wins that a player has. And we're trying to figure out whether we think they're going to be inducted into the Baseball Hall of Fame. And it actually, despite its simplicity, it works reasonably well. Brian Mills and his co-author have a more serious attempt at this if you're interested. But again, the point here is just the example. So is this classifier fair with respect to batters and pitchers? If we define the protected class as are you a batter or are you a pitcher, and yes, Babe Ruth causes problems here, but and someday Ohtani will as well. But if we use that as the protected class, again, we can show that actually all three of these criteria are close to 0. And so it does appear that, at least in the case of this classifier, that it's fair with respect to batters and pitchers. Again, the base rates are the same. That is, batters and pitchers are inducted into the Hall of Fame at relatively equal rates. But if you look at only pitchers and you look at starters and relievers, you see something different. You can see that with respect to independence and sufficiency, you have relatively low scores. But with respect to separation, you actually have kind of a high value there. So again, it's just an illustration of how this kind of technique might be useful in helping us think about whether the things that we're talking about are fair or not. OK, this is a different example, a slightly more complicated example, based on real data and a real paper. So in the Texas Ironman, men and women compete. There's a professional division. And a naive way of thinking about who deserves to win a prize in this competition might be, I just want to take the fastest 20 people. I don't care about gender. The status quo, what they actually do is they take the fastest 10 in each gender division. And then the paper, the Martin's paper, proposes a method for computing what they call a quotient. Well, it is a quotient. But it's the time relative to the world record for that gender. Right? So they're looking at that quotient, and then they want to organize it based on those times. So if you think, so this is the code here. If you think about what is happening here, so we have the actual times along the x-axis here, men and women separated by color, and that black line represents the 20th fastest time in the overall competition. And so again, in a naive world in which you're ignoring gender, you can see that only men would win prizes. The top 20 finishers would win. And I guess I hope we can all agree this doesn't seem quite fair. And so that's why it's not what people do in practice. And that looks more like this, where you have two different boundaries. One that's cutting off kind of the 10 fastest men, another that's cutting off the 10 fastest women. And now we can think about, is this more fair? In the paper, they're looking at these quotients that they're computing. And so the boundaries come actually now on the vertical axis. And so there are people who would have won a prize under one system who will not win a prize in the other system, and vice versa. Right? And these become, in the context of this machine learning framework, these become the errors, the discrepancies between the y's and the y-hats. So what we can say using the machinery that we built is, so you can look at the independence, but actually if you compare the naive model of just the 20 fastest people, you get NAs for the others because it's only men that won, right? And so you have division by 0 here. That doesn't help us so much. But if you compare the status quo to the proposed method, you start to get some numbers that I think have some meaning. And interpreting what that meaning is kind of tricky, because I think it's natural to think about, well, is the system fair? But really what this is telling us is the system fair with respect to this other system, which may or may not be fair. So, but I think the numbers have meaning, right? So that separation number of 0.3 is a relatively high value, and that's telling you that these systems are they're making different kinds of errors, and we can think about sort of like, what does that mean? Do we think that this results in something that's ultimately more fair or less fair? But there is a quantification there. Okay, so that's kind of where we are. We're working on some visualizations in 2 dimensions, which may include ROC curves and calibration plots. The reason we called that function fairness cube is because I think there's a natural interpretation here where you're working in a 3-dimensional space with those 3 coordinates. And the origin is the thing that's totally fair, which is generally not going to be achievable in practice. But that's still kind of like the aspirational goal. So thinking about how to visualize that, is there a distance metric for overall fairness? And then, as Sarah alluded to, what we're currently doing, so what we've showed you today is only groups that have 2 levels. But I think the method will extend to groups that have more than 2 levels. Currently, the way that we're aggregating over that is taking the mean absolute difference. But that's just one way of thinking about how how differences between levels within a protected class can arise. So there may be other ways to look at that. And then, obviously, looking for more suitable applications. So if you have an idea, hopefully, hearing this talk triggers some synapses in your brain. If you have a data set or a situation that you are interested in and you think that maybe this could be applicable, please come talk to us. We'd be happy to look at it with you. And that's it. Thank you very much for your time.
We have time for a couple questions. Does anybody have any? Andrew? Yeah, sorry, in the back, yeah.
Elliot Schwartz, hi.
Elliot.
I'm a figure skating judge, so it's a little bit out of left field, but I've worked a lot of analytics and modeling with acrobatic judge sports. So just your first response is fine, and I'll follow up with you later. How would you think about fairness in judge sports? And how would you approach it as a statistical problem?
Yeah, okay, so the question was from a figure skating judge, and the question is about how do we approach the question of fairness in judged sports. So this is a great question. I was thinking about this the other day as we were trying to brainstorm a little bit. I think the hard thing here is there's no ground truth, right? So in order for any of this to work, you need like a Y that represents the actual truth and a Y hat that represents the judged truth. So that we have. But I'm not sure what the Y is. And if we could figure out something in that, then I think we would have something. But until then, it's hard to know.
And how would you approach the judging bias question?
Well, so then it's just assuming that you had the ground truth value, right? Then it's just a question of what is the protected class that you want to define, and then you run it through, and then I think you'd have something to think about and talk about. Yeah.
Thank you.
Yep.
All right, let's thank Ben and Sarah once more.